Hey guys, Mr. B here, and in this video we're going to be going over the chapter 11.2 practice problems. Alright, let's get started here with number 1. It says, write and balance the equation for the formation of magnesium nitride, Mg3N2, from its elements. Alright, so we're going to be writing out a reaction from the elements magnesium and nitrogen forming magnesium nitride. Okay, because it says for the formation of. So we're going to have magnesium reacting with nitrogen. And nitrogen is a Brinkelhoff, so it is diatomic, okay? And we're going to be making magnesium nitride, which they fortunately gave us a chemical equation for, so we don't need to write it out ourselves. And it's going to look something like this. Then we just need to balance it. And the only thing that is not balanced here are the magnesiums. There are 3 on the product side, so we need 3 on the reactant side. The nitrogens are already balanced out for us. So that's it for number 1. That's all we're doing, okay? It's a combination reaction. So we have this reacting with this, and we're making one product. All right, taking a look at number 2. It says, write and balance the formation of iron 3 bromide from its elements. Okay, so pretty much the exact same thing we just did. We're going to be forming iron 3 bromide from its elements. The elements are going to be iron and bromine. So iron reacting with bromine, which is a Brinkelhoff. And we are going to be making iron 3 bromide, which again, they give us the chemical formula for. So here are our reactants and our products. Then we need to balance. The bromines are not balanced. We have 2 on the left. We have 3 on the right. So there's no whole number that we can multiply this 2 by to make it a 3. So we're going to instead think of what's the first thing that 2 and 3 both multiply into that they have in common. It would be 6. So if we put a 3 there, that gives us 6 bromines. We put a 2 there, that gives us 6 bromines. And then this unbalances our irons. So we're going to put a 2 in front of the iron there to balance that back up. And there we go. There is our balanced chemical equation. All right, taking a look at number 3. Complete and balance this decomposition reaction. All right, so decomposition means that we are going to be breaking apart the compound, typically to make the elements that make it up or smaller compounds. So in this case, we have HI, which is hydroiodic acid, and it's breaking apart. So it's going to break apart probably into hydrogen, which is a Brinkelhoff, and iodine, which is also a Brinkelhoff. Okay, so H2 and I2. And then in terms of balancing, we'll need to put a 2 in front of the HI to balance out with the hydrogens and the iodines on the product side. Okay. And that's it. That's our final answer. That's all they're looking for. All right, number 4. State, as always true, sometimes true, or never true. In a decomposition reaction, there is a single reactant. So we're going to say that this is actually a little bit of a tricky one. We're going to say always true. Okay. Typically, yeah, decomposition, you have one single reactant and it's breaking down into smaller things. Yeah, so we're just going to say always true. I don't want to make it too complicated. So, all right, taking a look at number 5. And I've left my activity series here. You might want to be looking at the one on the back of your periodic table, but I left mine, the one here, so we can use it because we might need to use it. So, all right, it says complete the equations for these single replacement reactions in aqueous solution. Balance each equation. Write no reaction if a reaction does not occur. Okay, so there might be some of these ones where nothing happens, in which case our our activity series chart is going to come in handy here. All right, so we have FeS, so Fe solid, reacting with PbNO3 2. NO3 2, which is aqueous. All right, so it's a single replacement. So that means that the iron is going to replace the lead. Okay. Now, before we write this out, let's go check our activity series to see if iron is higher on the list than lead. Okay, and I have the note here. So if the element that is by itself is higher on the list than the element that is in the compound, then a reaction will happen. So the element by itself, again, in this case, is iron. The element in the compound is lead. So we have iron, Fe, that is higher on the list than lead, which is the one in the compound. So yes, this reaction will happen. So if it does, lead will be by itself, and iron will be paired up with nitrate. Now, we don't know what the charge on the iron will be because iron can be +2 or +3. It is a transition metal. It makes more than one charge. But based on this over here, this was lead +2. So it's likely that the iron will be +2. Okay, so we're just going to say that this is going to make iron 2 nitrate just because the lead was lead 2. Okay, and then in terms of balancing, we don't need to balance anything because it's already balanced out. So, all right, taking a look at letter B, we have Cl2, which is aqueous here, reacting with NaI, which is also aqueous. All right, so this one is one where we're going to probably have the nonmetal replace the other nonmetal. Now, unfortunately, again, chlorine and iodine are not on the activity series, but typically on our periodic table, the higher the element is on the periodic table, the more reactive. Okay, so as we go down the columns, things get less reactive. So chlorine is higher than iodine is. Okay, which means that chlorine is going to have the ability to replace the iodine. So in our products, we're going to have iodine by itself, and it is a Brinkelhoff. Okay, so it's I2, and we'll have NaCl then as our other product. And then in terms of balancing, we need to put a 2 here to balance out the the chlorines, and then a 2 there to balance out the sodiums. All right, taking a look then at letter C, we have Ca, which is a solid, reacting with H2O, which is a liquid. So in this one, again, it might be easier, and I think it is easier. So let's rewrite this. It's easier to actually write it as CaS plus HOH. Okay, it's easier to write it that way because basically we can see that it's hydrogen bonded with hydroxide. So the calcium will replace the hydrogen. Okay, now again, let's go check on our activity series to see, is calcium higher on the list than hydrogen? So let's take a look. So calcium is up here, hydrogen is down below. Yes, it is higher, so this reaction will happen. So we're going to have H by itself, and it is a Brinkelhoff, so it'll be H2, and then calcium will be bonded with hydroxide, and it's going to have a chemical formula of CaOH2, and that is because calcium makes a charge of +2 when it bonds with something. Okay, so it's Ca2+, and hydroxide is -1, so we need 2 hydroxides to balance with the 1 calcium. That's where the 2 comes from. Okay. Oh, exit. There we go. And in terms of balancing, so if we look, we can see that we have 2 hydrogens on the right, 1 on the left. So we need to put a 2 there. That will give us 2 hydrogens. It will also give us 2 OHs. And we have 2 OHs on the product side, so that balances out perfectly. And the calcium, we have 1 and 1. So our final balanced equation will look something like this. And if you want to rewrite the HOH as H2O again, you can. Okay. Sometimes it's easier to view it as HOH. It's easier to see sometimes. All right, looking at question number 6. Write the products for these double replacement reactions, then balance each equation. All right, so let's do a text box again down here at the bottom. And so the first reaction is NaOH aqueous reacting with FeNO3 2, which is also aqueous. All right. And so this is double replacement. So the sodium here is going to replace the iron, or the sodium and the iron are going to swap. So in our products, we'll have Na bonded with NO3, and we will have Fe bonded with OH. Okay, and it's going to look like this. Now, real quickly, but let me just go back for a second and let me explain the charges that are going on. Okay, so sodium is +1 and OH is -1. Okay, so when those two are bonded to each other, that's how we get this chemical formula. The other one we have is iron, which is Fe. Now remember that iron can make a bunch of different charges, so we actually don't quite know what it is. However, it is bonded with nitrate, which is NO3, and that is -1. Okay, but we have 2 of them here. We have 2 of them. So total, this is going to be -2 from both nitrates, which means the iron is going to be +2. Okay, so that's how I know that it's iron 2 nitrate. So when we rewrite our formulas as our products, we have Na. So Na, which is +1, bonding with NO3, which is also -1. So since those are +1 and -1, those just balance out with each other. So we don't need any other subscripts. And then as for the iron hydroxide part, we have Fe 2+. We know it's 2+ because we figured that out over here. And that's going to bond with hydroxide, which is OH -1. Okay, so that's how I know that the formula needs to look something like this. There needs to be 2 hydroxides for bonded with the 1 iron, because the 2 hydroxides will have a charge total of -2 to bond with the 1 iron that's +2. Okay, so that's how I know that that's our chemical formulas for those. And then we just need to balance. In terms of balancing, we have 1 sodium on the left, 1 sodium on the right. That's balanced. We have 1 hydroxide, so 1 OH here, but we have 2 of them on the right. So that's not balanced. So we need to put a 2 there to balance out our OHs. That also now is going to give us 2 sodiums. And on the right-hand side, okay, so we have 2 sodiums on the left. On the right, we only have 1. So we need to put a 2 there to give us 2 sodiums. That also now is going to give us 2 NO3s, or 2 nitrates. But on the reactant side, we already have 2 nitrates. So that's balanced out. And then we have 1 iron here, and we have 1 iron there. So those are going to be our products. And the very final thing we need to do here is check to see if one of them is going to be a solid or a precipitate. Now it does tell us iron 3 hydroxide is a precipitate. So that would be this one here. But we're going to check just in case. Okay, so this is iron 2 hydroxide and sodium nitrate. So let's go take a look at the back of our periodic table. We're going to take a look at the solubility table part, which is the upper right. Okay, so we have iron. What did we have? We had iron 2 hydroxide and sodium nitrate. All right, so let's go take a look. So iron 2 is here. Hydroxide is here. So if we line these up, that says solid. So beautiful, that one is a solid. The other one we had was sodium and nitrate. If we look at those two, we get aqueous. All right, so we have a solid, which is good. Remember that we need to either make a solid, or we basically just need to make something that is not both aqueous. And in this case, we have a solid. So that is our final answer here. Everything written out properly with the solid part identified. Okay, so let's take a look at letter B. So we have BaNO3, and this is in parentheses. So NO. Oh, what did I just do? My bad. Sorry. BaNO3 2, and that is aqueous, reacting with H3PO4, and that is also aqueous. All right, so again, double replacement. So the barium and the hydrogen are going to swap. So we will have, and again, let's write our ions so we know. So barium is a Ba2+, bonded with nitrate, which is NO3 -1. Okay, that's how we get this chemical formula up here. As for this, we have H, which is +1, bonded to phosphate, which is PO4, has a charge of 3-. Okay, so when the barium switches and bonds with the phosphate, we have barium, which is a charge of 2+. So, oh, my bad, did not mean to do that. So we have barium, which is 2+, bonded with phosphate, which is 3-. Okay, so we have to balance our charges. We can do our Wonder Woman. So we can drop and switch the numbers. So the 3 from this is going to go down onto the barium, and the 2 from this is going to go down on the phosphate. So we're going to have Ba3, and then in parentheses, PO4, and then a 2 outside. Okay, so there's that chemical formula. And then as for the other one, we're going to have H bonded with NO3. So H is +1, and NO3 is -1. So those are just +1, -1. They would balance each other out just fine. And so our chemical formula would be HNO3. Okay, so those are our two products. We can balance this real quick too. So we have 1 barium on the left, 3 bariums on the right. So we need to put a 3 here. Okay, that'll balance out our bariums. That now is going to give us 6 nitrates. Okay, we have 2 there times 3. That's 6. Here we only have 1 NO3. So we're going to put a 6 there to give us 6 nitrates. That now gives us 6 hydrogens here. And over here we only have 3. So let's put a 2 to give us 6. That also then gives us 2 phosphates or 2 PO4s. But we have 2 PO4s right there. Okay, so everything is balanced out. Last thing now is to check, is one of them going to be a solid? Let's check on our, let's check on the back for periodic table. So we are looking for barium phosphate. So barium and phosphate is here. So we have barium and phosphate, and this is a solid. So that's perfect. And the other one is technically nitric acid, HNO3, and all acids are aqueous. So that one we don't really need to look up, but we already saw that this one is a solid. And once you figure out which one is a solid, the other one is definitely not going to be. Okay, you're never going to have 2 solids. It also says here that barium phosphate is a precipitate, which I didn't read before. So in the problem, it also tells us which one. All right, so that is that one there. Let's delete this slide here that we accidentally made. Let's take a look at the last problem here. Number 7. It says write a balanced equation for the complete combustion of glucose. All right, so we have a combustion reaction here. So we're going to have C6H12O6. Combustion means it's going to be reacting with oxygen. And the two products we're making are going to be carbon dioxide and water. Okay, so this is going to be our combustion reaction. And pretty much other than this, which they give us at the beginning, this part is the same for every single combustion reaction ever. Okay, stays the same. So really all we have to do here is just balance it, because predicting the products is very simple because the products are always the same thing. So balancing these are the tricky ones, because this is where we have oxygen in multiple places. So let's get a count of everything. So we have 6 carbons, 12 hydrogens, and we have 6 oxygens here and 2 oxygens there. That is a total of 8 oxygens on the left side. Okay. On the right side, we have 1 carbon, we have 2 hydrogens, and we have 2 oxygens here, 1 oxygen there. That is a total of 3 oxygens. All right, so it's best to balance the oxygens last, just because they're in 2 different places. It can get tricky. So let's balance the oxygens last. We'll balance the carbons and the hydrogens first. So first here we have 6 carbons on the left, 1 on the right. Let's put a 6 there. That'll give us 6 carbons. Okay, it's going to change our oxygen number, but we'll take a look at that later. Let's move on to hydrogen. We have 12 on the left. We have 2 on the right. So let's put a 6 there. That will give us 12 hydrogens to balance those out. All right. And then as for the oxygens, okay, so let's count now. We have 6 times 2, that's 12. And then 6 here times 1, that's 6. So we have 12 oxygens here plus 6 oxygens there. That gives us a total of 18 oxygens. And on the left, we only have 8. All right, so we need to get 18. Now, if we put a number in front of this whole compound here, this C6H12O6, that's going to mess up both our carbons and our hydrogens. So let's try to not do that, okay? If we put a number, however, just here, that only changes the oxygen number. So we have 6 oxygens there plus 2 oxygens here, and that needs to be equal to 18 oxygens total. Now, we're going to multiply this 2 by some variable to get it to be 18. Okay, so we're going to put an x there. So the question is what number do we need to put in front of the oxygen to make it 18, right? So 6 plus 2 times something gives us 18. If we can get this to be 12, right? So 6 plus 12 equals 18. That means that the x is going to be a 6. So 2 times 6, that gives us 12 oxygens plus the other 6, that gives us 18, which means if we put a 6 there, That will get us a total of 18 oxygens on the left-hand side, because we have 6 here, and then 6 times 2 is 12. 12 plus 6 is 18. That balances out the 18 on the product side. And there we go. Our whole reaction is balanced. All right, guys, that was the last problem here in this section of notes. Hopefully that helps you. I know that these can be challenging. So again, as always, please, please, please reach out to me if you need help. We can go over more examples in person, or just chat about things and make sure that you're not confused. All right, that is it for this section. I will see you in the next one. Bye.